Hello everyone, this is Jeff at Material Energies with another video about Material ECA. At Material Energies, we develop Material ECA to do professional fitness for service and engineering critical assessments of complex, real-world issues quickly and easily. This video is the first of three describing the Material ECA Fracture component. After this series, you'll understand the options available in the fracture component, allowing you to conduct your application-specific assessments confidently. Part 1 will examine and demonstrate the component's options and features. Specifically, we'll see how to input a stress-strain curve, plot custom charts in Excel, assess materials with non-homogeneous toughness, and more. Part 2 will examine the solver and the solver's results. I received questions about the non-unique solution I showed in the introduction video and how I recommend processing or smoothing the critical flaw size results and using them for the max flaw size and fatigue components. Also, one user showed me a comparison he made between the results from the Material ECA solver and those produced by another commercial software product. I found that comparison insightful, so I'll show you that too. Finally, Part 3 will show how you can programmatically produce components as JSON data that can be easily uploaded into Material ECA. Doing this reduces the time to conduct multiple assessments by orders of magnitude and improves quality and confidence. We'll also see how to programmatically access Material ECA results for your own data-driven solutions, such as inspection planning, training neural networks for predictive analytics, and life extension. Before we get started, I have a few messages. I've added a page describing Material ECA on the Material Energies website. It provides links to the Material ECA app and YouTube page. Please check it out. I hope you find it helpful. A link to the page is in the notes below. Finally, I want to let you know that I'm updating the fatigue component in the next week or so. I received several requests for this update, as it will improve overall flexibility by allowing custom Paris Law fatigue crack growth inputs. Unfortunately, this input will make it necessary for users to update any existing fatigue components you might want to run again. I'm making sure that if a user tries to run an older component, it won't run, and the user will receive a notification. The update to each fatigue component will be straightforward and quick. It should just take a few seconds. If you're like me, you might have many fatigue components that need to be updated, and updating so many may be tedious. For that I apologize, but I expect you'll find the update to the fatigue component will be sufficiently beneficial to make it worthwhile. If you have any questions or want to share your experience using Material ECA with me, you can find my contact information on my website, materialenergies.com, or you can email me at info@materialenergies.com. As discussed in the introduction video, Material ECA encapsulates functionality as components, which enables flexibility and expandability. In this video, we'll examine the fracture component. The fracture component automates the calculations of the 2019 version of BS 7910, where the material toughness is assumed to be a single value. The methods and terminology used in the fracture component are generally based on those in BS 7910. Users should have their own copy of BS 7910 and be sufficiently familiar with the document. For a given flaw, the fracture component calculates three values: the fracture ratio, the load ratio, and the failure assessment line. The results are visualized on the failure assessment diagram. The assessment point is associated with the load and fracture ratios. The flaw is acceptable if the assessment point lies beneath the failure assessment line. The flaw is considered critical if it lies on the failure assessment line. The fracture ratio is based on the stress intensity factor and the toughness value. Since the stress intensity factor varies along the perimeter of the flaw, Material ECA calculates multiple values of the fracture ratio and uses the largest value. However, in some cases, BS 7910 limits us to two values associated with the surface and deepest points. The load ratio is based on the reference stress and the yield strength, and Material ECA calculates only one load ratio value. Okay, let's go to Material ECA and look at the fracture component. Okay, we've entered the app by going to app.materialeca.com, signing in, and let's enter the live demonstration project we built during the introduction video. In here, we'll duplicate the first fracture component and provide a new name. To start, I'll go through the form and we'll discuss each of the inputs and the options. Once we go through the form, then I'll demonstrate some of the features. First off, there are 7 geometry types. There's the plate, where we can use surface or embedded flaws, corner flaws in plate, circumferential flaws, surface or embedded on the outside surface or the inside surface, axial flaws on the outside surface or the inside surface, both surface and embedded, on cylinders and pipe, and straight flaws in round sections. We're going to stay with what we used originally, the circumferential ID flaw. We'll put in a wall thickness. We're going to automatically allow Material ECA to calculate the section width. It does this by looking at the internal circumference for ID flaws, and for OD flaws and for near OD flaws, it'll look at the mid-wall circumference. So we need to put in a diameter. Let's put in 10.75 and we'll select inches. KM, we'll use 1.2, KTM, KTB, and KM. These 3 parameters are all consistent with BS 7910. The KM value will also modify the reference stress, goes into the load ratio calculation. In the same way that the KM value affects the bending stress in the stress intensity factor calculations. The KTM and KTB values do not impact the reference stress calculations. We'll put an attachment length, we'll assume 10. When we put in a value for attachment length, we have a choice of using the 3D MK solution. What Material ECA will do is when you click run, it'll check to see if the 3D solution is applicable. If it is, it will use it. If it's not applicable, then it will default to the 2D solution. Loading, primary membrane, and bending are consistent with BS 7910. The only constraint is that the sum of the 2 values must be larger than 0. Secondary membrane and bending stresses can be manually input, or down below where we have an option to relax the weld residual stresses, you can just ignore these for now. And Material ECA will go in and automatically use the yield strength that you input under the material section and relax it accordingly. And then it will leave a value for 0 for the secondary bending stress. So we'll leave that empty for now. We'll place the specified minimum values for X65 pipe in the material properties, 450 megapascal, 535 for tensile, and the equivalent for 30,000 KSI for the elastic modulus and 0.3 for Poisson's ratio. We'll leave the loiter strain plateau alone for now, and we'll use a stress strain curve. So let's select that. We want to paste the stress strain curve. I have a stress strain curve expand this box so that we can see it. What's important to know is when you input the stress strain curve values, first off, these are the engineering stress strain values. The first point must be 0, 0. So 0 stress, 0 strain. The stress values on the left, the strain values on the right. We're using units for stress of megapascal and units of strain dL over L. The stress values must not incrementally decrease. They're allowed to remain the same, so you can include a Loiter's plateau. The strain values must incrementally increase. Once we put in these values, we can view the curve, take a look at the points that are selected, confirm we have the correct units. Comes out to about 15%, 0.15 in this unit. They all look good. Then we could check the validation, and we can see that the points are valid. So we can go ahead. For toughness, we can choose between a stress intensity value, J integral value, or CTOD. Let's choose stress intensity. We'll use units of megapascal root meter, and we'll put in a value of, let's say, 200. We'll use that for both surface flaws and embedded flaws. We're allowed to put in 2 different values depending on the surface or embedded flaws in case you want to have a different value based on, for example, an environmental condition that makes the surface toughness a little bit different. We also have the ability to add multiple values of toughness for surface flaws. By clicking this new line button, I can put in a height of, for example, 3 millimeters and use a different toughness value, say 120. This way, this might simulate some clad piping where we have a toughness value of the alloy 625 from the surface at 0 to 3 millimeters, and then a lower toughness value associated with the carbon steel substrate material starting at 3 millimeters on out. We'll ignore this for now, and we'll demonstrate this later on. Then we have options. The first fracture setting is to choose to use the M7 solutions if they're applicable. These are applicable for the circumferential and axial flaws in cylinders and plate. When you select this option, Material ECA, when run, will check to see if the M7 solutions, the pertinent M7 solutions, are applicable. If they are, they'll use them. If they're not, they'll default to the M6 solutions. So I normally keep this selected. The next option is the Neuber method, which is used to adjust the KM parameter. Requires a stress strain curve to do this. This calculation is done consistent with the method described in DNV RPF 108 for certain conditions. I'm going to leave that off for now. And here's the option for relaxing weld residual stresses. We discussed that earlier. And I mentioned earlier how the stress intensity factor and the fracture ratios will vary around the perimeter of a flaw. The default value is to calculate 46 different values. That's at 2-degree increments from the surface to the deepest point. But any value can be put in there between a minimum of 2 and a maximum of 1,000. When you do the calculations, Material ECA will automatically take the largest value. The plasticity interaction parameters, BS 7910 gives 2 options, and Material ECA allows you to choose either the V or the rho. And you also have a choice of putting in 3 different failure assessment diagrams. The option 1 continuous, option 1 discontinuous, which requires a Loiter's plateau, and the option 2, which requires a valid stress strain curve. We have that, so we'll select that now. We can have a choice of putting in our own maximum load ratio value for the failure assessment diagram. I'm going to turn it off, and I'm going to allow Material ECA to calculate the appropriate value. We can save it, and we can run it. Now let's first run a surface flaw. I'm going to set a flaw height of 3 millimeters by 15 millimeters, and by leaving the flaw ligament at 0, Material ECA will recognize this as a surface breaking flaw. Select Run, and it run. Let's take a look at the results. Okay, the results were acceptable. We have our fracture ratio, our load ratio, and the critical angle was at 90 degrees, so that's the deepest point. We can see that the stress intensity factor selected was the M7 solution, M7.3.2, and the reference stress selected was NXP 9.2. And we have our initial and final flaws, which are the same for the fracture component. They would be different for where there's flaw growth in the fatigue and ductile tearing components. And we can see the failure assessment diagram. By hovering over the lines, we can see each of the points and look at the values. Hover over the assessment point to see the values are the same. It's acceptable because the point is below the failure assessment line. Then we can see some of the details. We can see that the section width used, that calculated, was 732 millimeters. You can see that the secondary membrane stress was relaxed from 450 megapascals to 244, and none for the secondary bending stress. We have input for the reference stress, what I call alpha double prime, and the load ratio max value used, and the toughness value used. Down below we have a table with 46 entries, one for each of the fracture ratios calculated. This table, the first column is the flaw angle in units of radian. So the first point is the surface point. The fracture ratio calculated was 0.34. We can go quickly to the bottom of the table and look at the deepest point and see it's got a fracture ratio of 0.36, and so that's the largest value. Now you notice that other than the surface and the deepest point, the fracture ratios are all returning zero values. That's because above we see the solution was the M7 solution, and that only calculates the surface and the deepest points. So there's no fracture ratio. You can see that the MM and MV values for any data points other than the surface and deepest points will return zero values. Looking farther over to the right, we see this column where it says MK is 3D, and it's true. This means that it automatically saw that the 3D MK solution was appropriate, so it selected it. And it calculated MKM and MKB values according to the 3D solution. Again, the MKM and MKB values are zero unless you're at the surface point or at the deepest point. Again, the MK's 3D solutions are only applicable for the surface and the deepest points. Now we can go and take a look at the report, where the fracture results show a detailed listing of all the calculated results. The fracture report only shows a summary of the results, but it lists all the input associated with the calculation. So this is perfect for documenting the calculations that are done. You can save this as a PDF file and attach it to a report or hand it to a client for verification purposes. But let's go back to the results, and we can scroll down and let's export the results to Excel. Open the file. The results in Microsoft Excel are a little bit more comprehensive than what's even in the reports. Lists all the possible results here. You have the initial flaw size, the final flaw size, the failure assessment line, the table of the fracture ratios, including all the details on this sheet for fracture results. On the next sheet for fracture input lists all the input that went in. Let's plot the failure assessment diagram. So I'm going to grab this, the failure assessment line. Insert charts, put in all the points, move this to its own sheet. Give the axes a name. And let's add the assessment point. LR, KR, and here's our failure assessment diagram with our assessment point. Now, let's go back to our component and let's run this component using the solver. And we'll get the critical flaw size. We use high resolution, keep it in a surface flaw, run solver, and let's take a look at the results. Now the solver works by looking at assessing an array of flaw sizes, starting at the origin, radiating out at various different angles until it reaches an unacceptable flaw, and it cuts back to ever finer. And when you do the high resolution, you'll end up with, I think, 100 points along the critical flaw size curve. So let's export these results to Excel. Open up the solver results. Take a look at the critical flaws, and we'll grab them. Copy them, and we'll move them. We'll create a new sheet. In this one, we'll call this critical flaws. Paste. I'm going to change the order of the rows because it's easier for me that way to have the flaw length on the left side. I'm going to insert a chart again. We'll move this to its own sheet. And let's put in the assess flaw. And let's take a look at our critical flaw chart. Now we can compare the failure assessment diagram, showing it's acceptable, and we could also look at the critical flaw chart where we can see what the assessed flaw is relative to how large the critical flaws are. I find this chart to be more pragmatic than the failure assessment diagram. Okay, let's go back to the component. And this time we'll run it using an embedded flaw. Come down to the bottom, select run, and this time we'll put in a flaw that's 5 by 15 by 3. So we have an embedded flaw with a ligament of 3 millimeters. Click run. Let's take a look at the results. You can see the results are acceptable. We have the KR, LR values. The critical flaw angle is at 90 degrees, so it's the deepest point. We can see a different stress intensity factor solution, M45 this time for embedded flaws, and reference stress, the P52. Critical flaws, we're still using the same failure assessment line, but a new failure assessment point. The same assessed section width, but we have new values for the secondary membrane and bending stresses, reference stress, and alpha double prime. Coming down to the stress intensity factor details for each angle, we can now see that we have fracture ratios, KR values, at each angle, down to the deepest point, 0.29. And that's because of two things. Now we're getting proper calculations for every flaw angle for MM and MB, and also the MK 3D solution is not the 3D solution. It's marked as false. So it's defaulting to the 2D solution, which allows for MKM and MKB values to be calculated at each of the assessed points. Again, we could look at the report, look at the input that was put in. To verify all this, we can save it as a PDF, and we can also export to Microsoft Excel the same way. We'll skip that for now, but let's go back to the component and run the solver for embedded flaws this time. Come to the bottom, click Run Solver. Again, we'll click High Resolution, but this time we'll select embedded flaws, and we'll use the same ligament, 3 millimeters, because we're selecting millimeters. Run the solver, and let's take a look at the results. They're still running. Hit refresh, and they're done. Now again, what happens, it calculated this array of flaws, and there are over 3,000 assessments done in the high resolution. Each of these points, you can mouse over them. You can see what the flaw length, the flaw height, and the ligament. Every one of these points will have a ligament of 3 millimeters. You can export these results to Excel as well. Now let's see what happens when the Annex M7 solution is not applicable. So let's change the outside diameter from 10.75 inches to 30 inches. We'll scroll down to the bottom, save, run, 3 by 15. We'll stay a surface breaking flaw, run. Let's take a look at the results. The results are acceptable, KR, LR value. The critical flaw angle this time is 0 degrees, so it's a surface point. And we can see the stress intensity factor solution used was the M41, the plate solution, and the reference stress, P92. The failure assessment diagram. And of course, the section width used is substantially larger this time because we're using a much larger outside diameter. Now let's demonstrate non-homogeneous material toughness input. We'll go back to the component, and we'll simulate an assessment that might be done for internally clad pipe, as we mentioned before. We'll set the OD back to 10.75 inches. And we'll come down to the toughness input. We'll add a new line with a start height of 3 millimeters. We'll put in a value of 120. So we're using two toughness values for a surface flaw. From the surface down to 3 millimeters, we're using a toughness value of 200 megapascal root meters. And from 3 millimeters on deeper, we're using a lower value, 120 megapascal root meters. And let's save this and run it. We use a flaw a little bit bigger. Let's use a 5 by 10 surface flaw. Select Run. Let's take a look at the results. It's acceptable. We have KR value, LR value. The critical angle is at 90 degrees, so that's the deepest point. You use the M732 solution for a stress intensity factor and the P92 solution for reference stress. And we can see the failure assessment diagram. Now let's take a look, most interestingly, at the stress intensity factor details. So on the surface, at 0 degrees, we get a fracture ratio of 0.382, and we come over to the column labeled K-mat, we get a toughness value at that point is 6324. That's in megapascal square root millimeter units, because all these are in the base units, which are megapascals and millimeters. So let's take a look at the deepest point. And at the deepest point, we have a K-mat value of 3794. So it's different, it's lower. We're using a lower toughness value for this point. In fact, we're using a lower toughness value for a number of points. If we come over here and look at the Z value, this is the distance from the surface used in the MKB calculations. Let's see if we can find where the transition occurred. Not yet, still in the 3000s. Here we go. This value is at 3794 and this one's in 36, and we can see that the transition happened right at 3 millimeters as expected. Now let's demonstrate how to use the Neuber method. This method is based on the procedure in DNV RPF 108. So let's go back to our component. We're going to stay with a single toughness value. We're going to increase the primary membrane stress to 425. Scroll down. We'll select the Use Neuber method to adjust to KM. Save. Run. 3 by 15. Surface flaw. Run. Let's see the results. And again, we have this. The results are acceptable. We have KR/LR values. This time LR is pretty substantial. Critical angle is 90 degrees. Use the same stress intensity and reference stress solutions. Value assessment diagram is shown. And this time we can see that the Km value used is different. We had input 1.2, so the Neuber method relaxed the value from 1.2 down to 1.04. In this video, we started taking a closer look at the fracture component by describing and demonstrating the input and options. This is the first of 3 videos dedicated to the fracture component. In the next video, we'll take a closer look at the solver and the solver results. And in the final video, we'll take a closer look at programmatically generating input from Material ECA and processing results from Material ECA. I hope you found this video helpful. Thank you very much for watching.